Imagine standing in a vast cathedral, its architecture invisible to your eyes. You can see the windows, the pillars, the individual stones, but you cannot see the framework holding it all together. You know it must exist, because without it, everything would collapse. Yet it remains hidden, defining everything while revealing nothing. This is our universe. In 2014, astronomers accomplished something extraordinary. For the first time in human history, they photographed the invisible architecture of the cosmos itself. What they captured wasn't made of matter as we know it. It wasn't made of light. It was something that occupies 95% of the universe's volume, yet had never been directly observed. The photograph revealed a bridge of pure matter spanning 6 million light-years through absolute nothingness, connecting two galaxies like a gossamer thread in the cosmic dark. This bridge shouldn't exist according to everything we thought we understood about empty space. But it does exist, and it's not alone. What if I told you that galaxies aren't scattered randomly through space, but are trapped like dewdrops on an incomprehensibly vast spider's web? That this web spans the entire observable universe, contains more mass than all the stars and planets combined, yet remains almost entirely invisible? That you, right now, exist inside one of its strands? Today, we journey through evidence that challenges everything we thought we knew about the universe's structure. Prepare yourselves. We begin. In 1989, astrophysicist Margaret Geller stood before a computer screen at the Harvard-Smithsonian Center, looking at data that made no sense. She and her colleague John Hutra had just completed the most comprehensive map of galaxy positions ever created, plotting over 1,100 galaxies and their distances from Earth. What she expected to see, galaxies distributed relatively evenly throughout space, perhaps with some minor clustering here and there. What she actually saw made her question whether her equipment had malfunctioned. The galaxies weren't scattered evenly. They formed something that looked disturbingly familiar, a pattern of walls, filaments, and enormous voids. Geller called it the Great Wall, a sheet of galaxies stretching 500 million light-years across space, with vast empty regions between them. It was one of the largest structures ever discovered in the universe. But here's what troubled her most. Structures this large shouldn't exist. The universe simply hadn't had enough time since the Big Bang for gravity to pull matter together into walls spanning hundreds of millions of light-years. According to every calculation, such structures were impossible, unless something else was organizing matter on cosmic scales. To understand what Geller had discovered, we need to rewind to 1933 to an astronomer named Fritz Zwicky studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. Zwicky measured how fast these galaxies were moving. He applied Newton's laws to calculate how much mass would be needed to keep them bound together at those speeds. The number he arrived at shocked him. The galaxies were moving so fast they should have torn the cluster apart billions of years ago. For them to remain gravitationally bound, the cluster needed to contain 400 times more mass than he could actually see through his telescope. 400 times. Zwicky proposed something radical. Most of the universe's mass was invisible. He called it dunkel materia, dark matter. The astronomical community largely dismissed his claim. It seemed absurd. How could most of the universe be made of something we couldn't see? But Zwicky was right. Over the following decades, astronomer Vera Rubin studied spiral galaxies, measuring how fast stars orbit around their centers. She found something impossible. Stars at the edge of galaxies move just as fast as stars near the center. This violates everything we know about orbital mechanics. In our solar system, distant planets orbit more slowly than close ones. That's fundamental physics. For galaxy edges to move as quickly as their centers, each galaxy must be embedded in a massive halo of invisible matter, extending far beyond the visible stars. This dark matter must outweigh all the normal matter, all the stars, planets, and gas by a ratio of 5-to-1. The universe we can see represents just 15% of the matter that exists. Which brings us back to Margaret Geller's Great Wall. If dark matter dominates the universe's mass, and if gravity pulls matter together over cosmic timescales, then dark matter must have its own structure, its own architecture. In the 1990s, cosmologists began running supercomputer simulations. They started with the conditions of the early universe, a nearly uniform soup of matter rippling with tiny quantum fluctuations. They let gravity do its work over billions of simulated years. What emerged from these simulations looked hauntingly familiar. The dark matter didn't clump into spheres or spread evenly. It formed a web, a vast interconnected network of filaments stretching across the universe with enormous empty voids between them. At the intersections of these filaments, where multiple strands met, dark matter pooled into massive nodes. The simulations predicted that normal matter, the stuff of stars and galaxies, would fall into this pre-existing dark matter web like rain collecting in a spider's web. Galaxies would form where the web was densest, tracing out its invisible architecture. This was the cosmic web theory. And here's what made scientists' hands tremble when they compared these simulations to Geller's observations. The simulated web matched the observed distribution of galaxies almost perfectly. The Great Wall wasn't a wall at all. It was a cross-section through one strand of an incomprehensibly vast web spanning the entire universe. But the evidence forces us to confront an uncomfortable possibility. If this web exists, if it truly structures everything at the largest scales, then it should leave signatures, observable traces, proof that could be detected if we knew where to look. The search for those signatures would reveal something far stranger than anyone anticipated.
Remember that 2014 photograph I mentioned? Let me tell you what astronomers at the University of Waterloo actually captured. They pointed their instruments at two galaxy clusters, Abell 222 and Abell 223, separated by 6 million light-years of what should be empty space. Using a technique called gravitational lensing, where massive objects bend light from background sources, they mapped the distribution of matter between these clusters. What they found was a filament of dark matter connecting them, a bridge of invisible matter containing the mass of 100 trillion suns, linking these two clusters like beads on a cosmic thread. This wasn't theoretical. It wasn't simulation. It was direct observational evidence of the cosmic web's filaments. The discovery sent ripples through the astronomical community. If you could see one filament, that meant the theory was correct. The entire universe must be threaded with these structures.
But astronomers wanted more than indirect detection. They wanted to see the web itself. In 2019, researchers using the European Southern Observatory's Very Large Telescope in Chile accomplished exactly that. They imaged individual filaments of the cosmic web directly for the first time using light from distant quasars. Here's how they did it. The filaments aren't completely empty. They contain extremely diffuse gas, mostly hydrogen, spread so thin it contains maybe 1 atom per cubic meter. For comparison, the air you're breathing contains 10 to the 25th atoms per cubic meter. When light from distant quasars passes through these filaments, the hydrogen gas absorbs specific wavelengths, creating what astronomers call the Lyman alpha forest, a pattern of absorption lines that reveals the web's structure. What they observed matched the simulations with unsettling precision. The filaments stretched for tens of millions of light years. They intersected at massive nodes where galaxy clusters formed. The voids between them were genuinely empty, vast regions containing almost no matter at all. One particular void they studied, the Bootes void, spans 330 million light-years across and contains only 60 galaxies. If it were as densely populated as the average region of space, it should contain 10,000 galaxies. Something carved enormous holes in the universe's matter distribution.
In 2013, astronomers made another disturbing discovery. They compiled data from multiple galaxy surveys, tracking the motion of thousands of galaxies across millions of light years. Galaxies aren't stationary. They move through space, pulled by the gravitational attraction of nearby matter. By measuring these motions, astronomers could map the distribution of mass, both visible and dark. What they found: galaxies move in rivers. Streams of galaxies, all flowing in the same direction, like currents in an ocean. These flows follow the filaments of the cosmic web, channeling along invisible pathways carved through space. Our own galaxy, the Milky Way, is moving at 630 kilometers per second relative to the cosmic microwave background radiation. That's 1.4 million miles per hour. We're not just orbiting within our local group, we're being pulled along a cosmic superhighway, flowing through one of the web's filaments toward a massive concentration of matter known as the Great Attractor. Analysis of these galactic flows revealed something profound. You can reconstruct the cosmic web's structure from motion alone. Watch where galaxies go, and you can see the invisible scaffolding guiding them. But this represents just one piece of a much larger puzzle hidden in the very light that fills the universe. In 2018, researchers analyzing data from the Planck satellite made a discovery that seemed impossible. They were studying the cosmic microwave background, light released when the universe was just 380,000 years old, now stretched by cosmic expansion into microwave radiation. This light carries a map of the early universe imprinted on it, tiny temperature variations representing density fluctuations in the primordial plasma. These fluctuations were the seeds from which all structure grew. The researchers discovered that these ancient patterns correlate precisely with the modern cosmic web's structure. The filaments, nodes, and voids we see today were already encoded in the universe when it was less than 1 million years old. Think about what this means. The cosmic web isn't something that formed recently. Its fundamental pattern was established in the first moments after the Big Bang, then spent 13.8 billion years evolving into what we observe today. The universe has been following a predetermined architectural blueprint since its birth. But here's where it gets strange. In the late 1990s, cosmologists calculated how many ordinary atoms, what physicists call baryons, should exist in the universe based on Big Bang nucleosynthesis. The number was definitive. About 5% of the universe's total mass energy should be normal matter. They could account for about half of it: the stars, galaxies, gas clouds, and intergalactic medium they could observe. The other half had simply vanished. For nearly 2 decades, astronomers searched for these missing baryons. They checked everywhere, between galaxies, around clusters, in giant gas clouds. Nothing. Then, in 2017, 2 independent teams made the same discovery simultaneously. They found the missing baryons hiding in the cosmic web's filaments.
Using X-ray observations and analyzing the slight temperature changes in the cosmic microwave background as it passed through space, they detected vast quantities of hot gas trapped in the Webb's filaments. This gas exists at temperatures between 100,000 and 10 million degrees Celsius, too hot to form stars, too diffuse to emit much light. The filaments contain 40% of all the ordinary matter in the universe. They're not just scaffolding made of dark matter, they're rivers of superheated gas flowing through the cosmic architecture, feeding matter to galaxies while remaining almost entirely invisible.
The most remarkable discoveries involve what's inside the voids, those vast, empty regions occupying most of the universe's volume. For decades, astronomers assumed voids were simply empty space, regions where matter never accumulated. In 2015, researchers studying void properties discovered something troubling. The voids are expanding. Not just expanding with the universe's overall expansion, they're expanding faster, actively pushing matter outward into the Webb's filaments. It's as if the voids themselves exert a repulsive force. This connects to one of cosmology's greatest mysteries, dark energy. Observations show the universe's expansion is accelerating, driven by some unknown energy permeating all of space. Most of this dark energy's effect manifests in the voids. The voids aren't empty, they're filled with dark energy's repulsive pressure, growing like bubbles in bread dough, pushing the cosmic Webb's filaments apart, stretching the architecture of the universe. Recent measurements indicate void expansion rates vary. Some voids grow faster than others. This shouldn't happen if dark energy is uniform. It suggests the voids might have their own structure, their own properties we don't yet understand. The evidence extends beyond simple observation, into the realm of cosmic evolution itself. The cosmic web isn't static, it's alive, breathing, constantly restructuring as dark energy inflates the voids while gravity condenses the filaments.
To understand why the universe organized itself this way, we need to examine what happened in the first moments after the Big Bang. The early universe wasn't perfectly smooth. Quantum fluctuations, random variations at the smallest scales, rippled through the primordial plasma. These fluctuations followed a specific mathematical pattern described by what physicists call a power spectrum. Here's where it gets fascinating. That pattern determined everything. Regions with slightly higher density attracted more matter through gravity. Over billions of years, these tiny differences grew into the cosmic web. Cosmologists at Princeton and Cambridge have shown that the web's structure is a direct consequence of initial quantum fluctuations amplified by dark matter's gravitational effects. The dark matter couldn't interact with radiation or normal matter except through gravity, so it began collapsing into structures immediately after the Big Bang. Normal matter remained trapped in radiation pressure for the first 380,000 years. By the time it could finally collapse under gravity, the dark matter had already formed the web's basic architecture. Normal matter simply fell into the pre-existing scaffolding. This is why the cosmic web is fundamentally a dark matter structure with normal matter decorating it, not the other way around.
Not all scientists agree on every detail. Three main interpretations compete to explain the web's finer properties. The cold dark matter model proposes that dark matter particles move slowly, allowing them to clump efficiently. This produces the hierarchical structure we observe, small structures forming first, then merging into larger ones over time. The warm dark matter hypothesis suggests dark matter particles have higher velocities, which would smooth out the smallest scale structures. This might explain why we don't observe as many dwarf galaxies as simulations predict. Modified gravity theories propose that dark matter doesn't exist at all. Instead, gravity behaves differently at cosmic scales than Einstein's equations predict. In this view, the cosmic web represents normal matter responding to modified gravitational laws. Current observations favor cold dark matter. The Planck satellite's measurements of the cosmic microwave background match cold dark matter predictions to within 1%. The distribution of galaxies, the structure of filaments, even the shapes of voids all align with this model. But here's what keeps cosmologists awake at night. We still don't know what dark matter actually is. We've observed its gravitational effects for 90 years, but never detected a dark matter particle directly, despite dozens of experiments. This forces us to reconsider fundamental assumptions about the universe. Either dark matter is made of particles so exotic they barely interact with normal matter, or our understanding of gravity itself is incomplete. Leading researchers at institutions like CERN, Fermilab, and the Kavli Institute are pursuing both possibilities. Some search for dark matter particles in deep underground detectors. Others test modified gravity theories against increasingly precise astronomical observations. The next generation of cosmic surveys will map the cosmic web in unprecedented detail. The Dark Energy Spectroscopic Instrument, DESI, which began operations in 2021, will measure positions and distances for 35 million galaxies across 11 billion years of cosmic history. This will allow astronomers to watch the cosmic web evolve, seeing how filaments formed, how voids emerged, how the structure changed as dark energy's influence grew stronger over time. The European Space Agency's Euclid mission, launched in 2023, uses gravitational lensing to directly map dark matter distribution. Over 6 years, it will create a three-dimensional map of the web's structure, covering 1/3 of the entire sky. These maps will reveal whether the cosmic web has hidden features, smaller filaments we haven't detected, fine structure within voids, variations in dark matter density along filaments. Each discovery will constrain theories about dark matter's nature.
Recent breakthroughs suggest the cosmic web doesn't just organize matter, it fundamentally shapes how galaxies evolve. In 2020, astronomers discovered that a galaxy's position in the web determines its fate. Galaxies and dense filaments receive constant streams of fresh gas, fueling ongoing star formation. Galaxies and voids experience isolation. They consume their gas over billions of years, then go quiet, producing no new stars. Our Milky Way sits in a relatively dense filament. The gas flowing along this filament has enabled continuous star formation for billions of years, including the formation of our Sun 4.6 billion years ago. But here's the unsettling part. The Andromeda Galaxy is approaching us at 110 kilometers per second. In roughly 4 billion years, our galaxies will collide. This collision isn't random, it's happening because both galaxies follow the same filament, flowing toward the same gravitational well. The cosmic web orchestrates galactic encounters across the universe. Every merger, every collision, every interaction between galaxies happens because the web channels their motions along predetermined pathways. Astronomers studying the cosmos field, a deep survey covering 2 square degrees of sky, found that galaxies separated by 50 million light-years along a filament are more likely to eventually merge than galaxies just 10 million light-years apart but in different filaments. The web's structure determines galactic destinies across cosmic timescales. In 2021, researchers made a discovery that opens entirely new possibilities. The cosmic web can transmit information. They found that disturbances in one part of a filament, such as a galaxy cluster merger, create gravitational waves that propagate along the filament structure. These waves modulate the flow of gas, creating patterns that travel at significant fractions of light speed. Think about what this means. The cosmic web isn't just scaffolding, it's a network capable of transmitting signals across intergalactic distances. Any sufficiently advanced civilization might use the web's filaments as communication channels, encoding information in gravitational wave patterns or gas density fluctuations. This connects to SETI, the search for extraterrestrial intelligence. Rather than searching for radio signals transmitted in all directions, perhaps we should look for modulated signals propagating along the cosmic web's filaments, visible only to civilizations connected to the same network. The implications are staggering. If the universe's architecture can transmit information, then it's not just a passive backdrop for cosmic events, it's an active medium that could, in principle, be used for communication or even computation at cosmic scales.
The most profound implications emerge when we consider why the universe has this structure at all. Some cosmologists argue that the cosmic web's properties seem eerily optimized. The filamentary structure maximizes matter distribution efficiency, concentrating material where it can form galaxies while maintaining vast empty regions where dark energy effects dominate. This efficient organization allows structure formation at all scales simultaneously. Planets form in solar systems within galaxies situated in filaments connected across the observable universe. Physicist James Gates at the University of Maryland discovered something unsettling. Certain mathematical equations describing fundamental physics contain what appear to be error-correcting codes, the same codes used in computer science to detect and fix data corruption. Could the cosmic web represent a kind of cosmic algorithm? The universe's structure emerging from information processing rules rather than simple physical laws. This idea borders on metaphysics, but it makes testable predictions. If the universe is fundamentally computational, then there should be a minimum scale, a pixel size, beyond which structure cannot exist. Interestingly, quantum mechanics does impose such limits through the Planck length. The cosmic web's structure also connects to multiverse theory in unexpected ways. Eternal inflation theory proposes that our universe is one bubble in an infinite foam of universes, each with potentially different physical constants. The process that creates new universes might be linked to void formation. Some theorists suggest that rapidly expanding voids could reach escape velocity relative to their surrounding space. If this happens, the void effectively disconnects from our universe, becoming its own separate spacetime, a bubble universe with potentially different properties. This is speculative, but mathematically consistent with Einstein's equations. If true, new universes might be constantly budding off from expanding voids within our cosmic web. We could be living inside one strand of a web that extends across multiple universes, connecting different realities through topological bridges we can't observe because they exist in higher dimensions. What ultimately happens to the cosmic web depends on dark energy's nature. If dark energy remains constant, the universe will continue expanding forever. The voids will grow. Filaments will stretch. Eventually, in trillions of years, galaxies will become so isolated that beings living in them will observe an apparently empty universe with no other galaxies visible. The cosmic web will have dispersed into nothingness, leaving only isolated islands of matter in an ocean of void. If dark energy strengthens over time, something more dramatic occurs: the Big Rip. Approximately 22 billion years from now, void expansion will accelerate until it tears apart the filaments, then galaxies, then solar systems, then planets, then molecules, then atoms themselves. The cosmic web would be the first casualty, ripped to shreds by runaway dark energy before individual structures even notice. But there's a third possibility, suggested by recent observations of void properties. Dark energy might not be constant. It might evolve, perhaps even reverse. If this happens, the voids could stop expanding and begin contracting. The web would condense, pulling all matter together into a big crunch. The universe's ultimate fate remains written in the cosmic web's structure, if only we can learn to read it correctly. We began with a photograph of a bridge, a strand of dark matter connecting two galaxy clusters across 6 million light-years of space. What we've discovered, that bridge is part of an architecture spanning the entire observable universe, an invisible scaffolding of dark matter woven through space, channeling matter into filaments, creating nodes where galaxies cluster, carving voids that expand and breathe with dark energy. This web was encoded into the universe 380,000 years after the Big Bang. It structures everything we can see. Every galaxy, every star, every planet exists where it does because the cosmic web placed it there. We live inside one of its filaments, flowing along predetermined pathways at 1.4 million miles per hour toward unknown destinations. The web shapes galactic evolution, determines which galaxies will merge, transmits gravitational waves across intergalactic distances, and might even connect to other universes through topological structures we cannot observe. Current scientific consensus agrees the cosmic web is real, it's fundamental, and it represents the largest scale structure in existence. But enormous mysteries remain. We don't know what dark matter is made of. We don't understand dark energy's nature. We can't explain why the web's structure seems optimized for complexity. Perhaps the most profound realization is this: we are not separate from the cosmic web. We are part of it. Every atom in your body was forged in stars that formed in the web's filaments. Your existence results from 13.8 billion years of cosmic evolution guided by invisible architecture. When you look at the night sky, you're not seeing stars scattered randomly through empty space. You're seeing lights on a vast web, a cathedral of dark matter stretching across reality itself, its complete structure still hidden from view. The universe is vast. The mysteries are endless. The journey continues.